So welcome to Math 150, lecture 32. And what I want to do today is I want to talk a little bit about differential equations. So again, we are towards the end of the semester. We worked really hard at the start of the semester. So your other classes can now work you really hard. I want to spend a little bit of a leisurely time for the last few classes, just talking about applications and what might you do next. We've spent all of this time learning this mathematics. What can you actually do with it? And so one thing is solving differential equations. Did we talk at all about solving, say, Newton's equation if the acceleration is constant? Did we talk at all about solving something like that? All right, so we can talk a little bit about that today. So a lot of physics comes down to, I have some quantities, I know how they change, I know something about how they're changing with time. If I know that, can I use that to deduce my solution? And so we'll talk a little bit about some very special cases of differential equations, and then as an application, we'll talk about solving a system of differential equations. So this is a great lead into both linear algebra, as well as multivariable, as well as differential equations. And as an application, we will apply this to the Battle of Trafalgar. So are there any history experts who know at all anything about the Battle of Trafalgar? Anybody know at least what war this is from?
The War of Northern Aggression?
No. I'm reminded of the great Simpsons moment when the bell rings on the last day of school and the kids are starting to run out, and the teacher goes, "Wait, we never finished World War II. Don't you want to know who won?" And the kids pause, and the teacher goes, "We did." It is not the War of Northern Aggression. Napoleonic Wars. So it is close enough. It is one of the most lopsided military outcomes, I think, in the history of warfare. And in terms of the impact, it was absolutely essential for what was going on in Europe at the time. All right, so let's start off with Newton. So we have F equals ma. dv dt is the acceleration, and dx dt is the velocity. So this is a very standard set of differential equations. So acceleration is the second derivative of distance. So d squared x dt squared is a of t. In the interest of time, I will only deal with motion of objects in one dimension, say just going straight up. With a little bit more work, we could actually make this a really multivariable calculus lecture and talk about what happens as an object travels in the Earth's surface, if you want to look at the projectile. So let's say we have the Earth's surface here, we have an object, and we have the force is mg coming down. G is about 9.8 meters per second squared. Have people seen enough physics to have seen problems like this? And the way you calculate the force is equal to G m1 m2 over r squared. The radius of the Earth is, I think, like 6,000 or so meters. Oh, sorry, 6,000 or so kilometers, something like that. So the radius of the Earth is about 6,300, 6,400 kilometers. Okay. So it's about 6,000 kilometers. If I move up 10 meters, the change in big R is negligible. This over here is essentially what the little g is. And if we are not really moving that far off the Earth's surface, it's essentially constant. If we're traveling to the moon, if you say it's constant, that's not a good analysis. But near the surface of the Earth, if I come up to the desk, no real difference in the force I'm feeling as I go up that small distance. So if we want to solve this, let's find velocity first. So we would get dv dt equals g. So we can write this as dv equals g dt and integrate. So we have the function 1 dv. What function as a function of v has derivative 1? B. What function as a function of time has derivative g? GT. And then we remember, oh, wait a minute, I have to do my constants. When I integrate, what function has derivative 1? V plus 5, 17. So I have to put a constant on the left-hand side. But I also have to put a constant on the right-hand side. Now, if I have a free constant on the left and I have a free constant on the right, I can put all the constants on the right-hand side and just have, say, C1 minus C2. Well, that's also a free constant. So I can just write it very nicely like this. And then if speed is V0 at time t equals 0, we get V of t is just GT plus V0. And this would be how you would solve for your speed as a function of time if you're just moving straight up and down. Now we want to find the location. So I could use x, but if I'm going straight up and down, what variable should I use? I should use y. So I could say dy dt is equal to the velocity, which we just showed is gt plus v naught. So dy would be gt plus v naught dt, and then we integrate both sides. Okay, what function has derivative 1 when I take the derivative with respect to y? Y. As we get y is just 1/2 gt squared plus v naught t plus some constant. If at y0 at time t equals 0, then we get y of t is 1/2 gt squared plus v naught t plus y naught. So hopefully you've seen solving differential equations like this in Calc 2. Depending on who's teaching it, sometimes differential equations is not covered at all. Hopefully you've seen some formulas like this in a physics class. They are sadly often done a la Moses coming down from Mount Sinai with here are the laws of kinematics equations, and this is where you are, with no justification as to this is why the particles move like this. This is why a lot of us cringe when physics is done before calculus, and cringe even more when it's done before algebra. Okay, the next level of complexity would be, what if we shoot something at an angle? So I could have, now I'll draw my surface of the earth like this. I shoot maybe from some initial height at some angle. So can somebody give me a situation where I might have something going off at an angle? Okay, jump, what else? Throwing a baseball. Given that we're going to talk about warfield later today, maybe a cannonball. And so you would have your initial height. You would have some height h. You would have your initial speed v. You would have some angle theta. And you have the force of gravity going down. And then what you would realize is there is only a force that's going to affect your vertical motion. The horizontal motion, if there's no friction, is going to just be constant. Yes.
Like letting a wind, right?
Yeah, that's what I said. Assuming no friction, no wind, nothing. So in the idealized case. And then what you would do is you would have basically two different things to solve. So you would have, d squared y dt squared is equal to negative 9.8. Because it's pulling you down. And you would have your initial speed, your initial height y naught, and your initial speed, say v sub y. And so I can write v as v sub x and v sub y. And this is going to be v cosine theta, and this will be v sine theta. And then I would have d squared x dt squared. What's the force in the x direction? Zero. And then I would have my x initial condition and my x initial speed. And so if you want to figure out how far does it go, well, you first solve the y equation to find how long is it in the air until it hits the ground. And that gives you the time, and then you feed that into the x. So I'll leave these as exercises if you want to go through and try to solve. These are really good things to try to do. Okay, but you would first solve the y equation and find how long is it in flight until it hits the ground. And then once you know that time, you then feed that into the x, and that would give you the horizontal distance. Okay. A natural question you might ask is, what is the optimal angle for it to go as far as possible? You're assuming no wind, no friction. Any guesses? 45 degrees, at least if h is 0. And so, there's a lot of really good questions you can have. If I want to see what's the furthest, what's my greatest range? And then, of course, you want to start taking into account, well, let me take account air resistance. And I think sometimes you have air resistance as linear and sometimes it's quadratic. It's been a while since I've done these equations. Does that sound right? And so the equations start to become more involved. And so as the differential equations become more involved, we have to develop either better techniques to solve them, or we resort to numerical approximation. And there are a lot of great algorithms to approximate solutions to differential equations. And with computing power available, as long as I can write down what the equations are, I can often just plug them and have them run through and come up with a really good approximation. If I want a better approximation, I have finer, smaller time step, and I do more calculations. So the question is, what kind of equations can we solve? So imagine I give you dy dt is just some function of t. And we know big F prime is little f. So imagine we know what the antiderivative of f is. Then I could say, oh, okay, then dy is f of t dt. Let's dt, and let's integrate both sides. And so I would get y equals big F of t plus some constant c. So as long as we can integrate f of t, we're in great shape. The problem is we might not be able to write down the integral of f of t in nice form. But this is why we have classes like Calc 1 and Calc 2, where we learn techniques of integration. So what are our techniques of integration? What can we do? Use substitution. What else? Integration by parts. What else?
Mathematical.
Mathematica, which is doing a lot of these. What else do we have? It's the least favorite technique. Trig substitution. I'm not going to say that trig is the least favorite. Trig is actually a special case of use substitution, but because of the very powerful trig lobby, they actually get their own name. Yeah, there's a trig lobby. They rotate between sine, cosine, tangent. The secant, cosecant, and cotangent just always discriminate against them if you get a chance to. It really is. Partial fractions. Partial fractions is the last technique that we have. And so a lot of times we can use those to evaluate f of t. But you've got to be a little bit careful. So let's say I give you dy dt is e to the t squared. So we get dy equals the integral of e to the t squared dt. So we could write this as e to the u is the sum and goes from 0 to infinity of u to the n over n factorial. So e to the t squared is the sum and goes from 0 to infinity of t to the 2n over n factorial. So if I integrate, I have the integral of the sum. What would you love to do to the integral of the sum? You're right. So you want to switch them. You want to switch the sum and the integral and do each piece. Which theorem is that? Which theorem allows us to say we never did it as an integral of the sum, we did it as two integrals. When can you switch the order? Yes, we want to use some kind of Fubini theorem. And then this would become the sum and goes from 0 to infinity, 1 over n factorial integral of t to the 2n dt. So that's just t to the 2n plus 1 over 2n plus 1 times n factorial. And now it's very fortunate we took some time this semester to talk about sequences and series and when they converge. You can use the root test, the ratio test, the comparison test, and you can show that this sum converges. So even though I can't write down a nice closed form expression for this, I can write down an infinite series that converges, and if I just take a couple of terms, it does a really good job. If I give you the function cosine of t, can you find a function who has derivative cosine of t? So what function has derivative cosine of t? Sine of t. So you might say, that's a much easier problem, because if I gave you cosine of t rather than e to the t squared, I would just say, oh, the answer is just sine of t. Well, how do you calculate sine of t? You have to use an infinite series expansion. It just happens to be an infinite series expansion that has a name attached to it, so we consider it a friend, and we consider this a nice, wonderful problem. We could give this function a name, and we could give its antiderivative a name. Its antiderivative has a nice explicit series. It's really not any worse than sine or cosine. And this is actually a somewhat important one. It's better if it's actually e to the negative t squared rather than e to the t squared. But this is a very important series. And so we can give it a name. And in fact, something very closely related to this does have a name called the error function. And it comes up in probability in terms of estimating and calculating probabilities related to the normal distribution. All right, so the last one I want to say is, in general, you'll have dy dt is going to be some function of y and t. And as they get mixed together, it's going to be very hard to solve. But you might be lucky, and maybe your function splits to a function of y times a function of t. How might you solve this? We did the special case earlier where f1 of y was just 1. And we just had dy dt was a function of t. And then it all came down to, if I can find an antiderivative, I'm done. Now I have this mix. I have y and t. How can I solve this? Thoughts? So if I write it as, dy is f1 of y, f2 of t dt, this is not set up yet to integrate nicely because I've got y's and t's on the right-hand side. What could I do? Yeah. Now, what do you have to be careful about if you want to be a mathematician? Yeah. If you're willing to be an economist or whatnot, but at least as a mathematician, you should at least pause and think, could f1 of y be 0? And if so, what do I do about something like that? And now we just integrate both sides. And so this is called a separable equation. I can separate it into a function of y times a function of t. And now it just comes down to, can I find the antiderivative of 1 over f1 of y? Can I find the antiderivative of f2 of t? If so, done, and I can solve it. So one of the classes you might take after this is differential equations, where you learn how to solve a variety of problems. And again, this goes back to the crying baby. The baby is crying. Why is the baby crying? Does the baby want to be held? Does the baby want milk? Does the baby want to watch the Red Sox? Does the baby want the Red Sox to be doing better? You start going through all the different things, and you try until finally you find something that works. And then after a while, you start to recognize this is the I'm hungry cry. This is the I want to be held cry. It's the same way with differential equation. I can write it as a product of two functions with all the y's together and all the t's together. I know how to solve something like that. And the more of these you do, the faster it is to stop solving. All right, so what I want to do now, because I have one more blank page before we get to the battle of Trafalgar, is I want to talk about another method of solving differential equations. What you notice is that the way we're really solving these is we're converting them to integral equations. And so I want to write down an integral equation that I first saw my freshman year from my physics mentor. He wanted us to have something to talk about over Thanksgiving. So define the integral symbol by the integral of f means integrate from 0 to x of f of t dt. Okay. So I'm defining my symbol like this. So this would be big F of x minus big F of 0, where big F prime equals the left. And I want to solve the integral equation, integral of f equals f minus 1, or the integral from 0 to x of f of t dt is f of x minus f of 0. Does anybody know what function works? I want a function such that if you integrate, you get back the function minus 1. And you can really view this as it's the function of x minus the function of 0. And I'm integrating my function from 0 to x. So it would be e to the x. So if you plug in f of x equals e to the x, it works. So I believe you use the method of divine inspiration, where you just write down the answer and then you can check and see that it works. We are not always divinely inspired. We will have to use divine inspiration later today. So let's just talk about how you might solve this. This is the same as if I subtract the integral of f from both sides and add 1 to both sides, as f minus the integral of f equals 1. Everybody comfortable with that? Yes. So this is the same as 1 minus the integral acting on f equals 1. Because it's just 1 times f minus integral times f. If you wanted to solve 5x equals 3, how would you solve 5x equals 3? 5x equals 3, how do we solve? Divide by 5 or multiply by another way of saying 1/5. Now, how else could you say 1/5? 5 to the negative 1. If I want to solve 7x equals 3, what do I do? Yeah, multiply by 7 inverse. So let's multiply both sides by the operator 1 minus integral inverse. This is classic physics, where you should be going, how the hell can you justify all the stuff that you, it can all be justified. So if I apply the operator 1 minus integral, and then I apply its inverse, where do I return to? Yeah, so the left-hand side is just f. And this should be inverse. So f is just 1 minus integral inverse of f. Recall 1 plus r squared plus dot 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 equals 1 minus r inverse. Right? When is that true? So when is 1 plus r squared dot dot dot, when is that equal to 1 minus r inverse?
When r is between 0.
A little bit more, absolute value of r less than 1. Because this allows complex values of r as well. Your statement is correct, it's a little bit more expansive. So take r to be the integral operator. So I now need to introduce something called the norm of an operator and show that the norm of this operator is less than 1, and then that this is going to be the inverse. I'm just trying to give you a sense of, if you continue with math, what might you see? There's ways to make all this figures. Okay, so this is the same as f is equal to 1 plus integral plus integral integral plus integral 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 plus dot 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 acting on f. I'm using the geometric series to expand this out. Okay. So let's do it piece by piece. One acting on, oh, I'm sorry, it's not acting on F, I'm sorry. This is a typo. It should be what? It should be 1. Fortunately, they can easily be fixed. All right, 1 acting on 1 is just 1. Now I have the integral acting on 1. That means the integral from 0 to x of 1 dt. What does that integral equal? So what's the integral of 1 from 0 to x? It's just x. Now the next term is I have the integral of 1. Well, the first integral of 1 gives me the function x. So I now just integrate from 0 to x the function of t dt. What is the integral of t dt? It is t squared over 2, and I evaluated x, so it's x squared over 2. But I don't want to write it as x squared over 2. I want to write it as x squared over 1. 2 factorial. Really, this is x over 1 factorial. The next term is integral of 1, which is the integral from 0 to x of t squared over 2 factorial dt. That's going to become x cubed over 3 times 2 factorial is x cubed over 3 factorial. And there you go. This has a lot of stuff that needs to be justified. But if you look at this, here's an interesting way of attacking some of these equations, and you're getting to the solution is the exponential function. So this is a great example of divine inspiration. If you happen to know the answer, you can just write it down. But what's the problem with divine inspiration? Yeah, frequently during exams, for instance, is a time when divine inspiration is sometimes fickle. And then the question is, are there other solutions? Maybe you're divinely inspired, maybe you didn't find all possible solutions. All right. So shifting gears, to the battle of Trafalgar, I'll have some additional stuff in the notes online, as well as links. If you want to read more about the battle, you can. Here's a list of the different sides. On one side, you have the fleets of France and Spain. On the other side, you have the United Kingdom. And I like how the result, it says British victory. It's more than a British victory. So if you look at the number of ships, 33 ships of the line for the French and Spanish, 5 frigates, 2 brigs, 35,000. British side, 27 ships of the line, 4 frigates, 1 schooner, 1 cutter, 20,000 men. About 4,400 killed on the side of France and Spain, 450 on the side of the British. 7,000 to 8,000 people captured. And here's the amazing part: no British ships were lost. 21 ships of the line were captured, and 1 was destroyed. The British fleet was stronger after the battle than before. Warfare is not like that anymore. In the middle of the battle, you're not really capturing. Or are you? If you look at the US withdrawal from Afghanistan, we did leave a lot of equipment there, which was then captured by the other side. So there is the complication of adding into the analysis. Is it possible for some of your forces to be taken over by the enemy and used against you? And the answer is yes. And it makes the calculation a little bit harder. It's much nicer when you know, okay, the quantities are going down with time, or at best, staying the same. But the British fleet was actually stronger after the battle than before. This is an incredibly lopsided victory. So England, Britain, this is an island kingdom. And so for them, the fleet is a necessity. So if you look at the analysis and the arguments in the world stage before World War I, Britain was very concerned about the rise of the German fleet. For a long time, Britain's philosophy was our fleet will always be strong enough to survive attacks by the second and the third strongest fleets in the world. And eventually reached the point where they could no longer do that. And they started allying with France and started making deals. We'll protect this part, you protect that part. And they were very concerned in trying to get Germany to do shipbuilding holidays. If you stop building, we'll stop building. And at one point, I think the Admiralty wanted 4 new dreadnoughts. I think Parliament wanted 6, and they had to sit down and negotiate. And they negotiated to 8. Is that when they were talking to each other, they goes, wow, the situation is more dire than we thought. 4 and 6 is not going to be enough. We need to go all the way up to 8. So this is one of the incredible examples of what can happen with superior forces and superior tactics. So not only do you win the battle, you've obliterated the other fleet at the same time supplementing your own. So we're going to talk a little bit about the mathematics behind this. So what was Nelson's battle plan? He was in charge of the British fleet. He basically had his forces coming in to the combined fleets from France and Spain. And the idea was to have the main part of the British fleet split off a good chunk of the French-Spanish ships and deal with them, while a smaller number of his ships would do a delaying action and just try to keep a bunch of the French and Spanish ships out of the main battle. And then after his main forces defeated the main part of the enemy fleet, he would then turn and help the other ships that were fighting and finish them off. So basically try to break this into 2 battles. Now, I do not believe that there is any evidence of Nelson or anyone in his command actually writing down differential equations and solving them. But this is a nice way of just trying to give a explanation of why might something like this work. So there's a beautiful paper, if you're interested, I can send you a copy, Mathematics and Warfare by Lanchester, and talks initially about classical warfare. So imagine you have 1,000 people fighting 1,000 people, or you have 1,000 people fighting 500 people, and after you fight those 500 people, you move on and you fight another army of 500. Does it make much of a difference if you have those 2 situations? Well, a lot of times what really matters is how many people can physically be involved in the battle directly. If you have 1,000 people, you might have deeper lines, but the number of people actually at the front of the battle, you may not really be able to get too much of an advantage of having more people because there's only so much contact you can have. So if the forces are equally trained, if you have 1,000 people fight 500 people, how many of the 1,000 do you think might survive? I'm sorry? 500. And then those 500 who survive then fight the other 500, and how many survive after that? 0. So if you have 1,000 fight 1,000, or 1,000 fight 500, and then fight 500 again, there's really no difference. In classical standard warfare, or basically just your sword on sword. You're not able to bring superior numbers to bear. I'll go to, in honor of Star Wars Day. Anybody know what movie? Spaceballs. So what was Doc Helmut's problem here? He had bad range, right? He wasn't able to hit Lone Star at all. So when we're trying to analyze things, go back to, so here is the more modern one with now dB/dt. So we're going to use blue and red so that no country feels bad. dB/dt, the rate at which the blue fleet is changing, is equal to minus R times C. The rate at which the red fleet is changing is minus B times K. Does it make sense that there's a negative sign? As time passes, as the battle goes on, your forces get smaller. So we're not allowing for capture of ships in a model like this. So we all agree that the negative sign is very reasonable. And what this is saying is the more red ships you're facing, the more losses you're going to take as blue. And similarly, the more blue ships you face, the more losses you're going to take as red. If I double the number of red ships, the rate at which the blue ships is decreasing is going to double. That's the model. And now the interesting thing is these constants C and K. These are the effectiveness. Do you think all combatants are equally effective. So if you go back to the Battle of Trafalgar in the early 1800s between the British and the French and Spanish, which ships do you think might be more effective? The British, why?
Because they ended up.
Well, looking at the data, we then see, what if you were thinking about the times, why might the British fleet be more effective?
They needed it more.
They needed it more, so they might have actually had more work in developing ships of the line, because it was absolutely essential to them. This was the argument they were making with Germany before World War I. For you, a fleet is a luxury. For us, it's a necessity. You're a land country. Imagine your ships have the ability to shoot accurately 2 miles further than your opponents, and your ships are faster. How much damage do you expect to have? None. Why?
Because their range.
Their range can't hit you. You can hit them. If they try to flee, what can you do? Chase them. And you can chase them while staying outside of their range. This is why we're showing the Lone Star clip. Doesn't matter. He might be extremely effective in that range, but if you can stay outside of his range, you're golden. This is why in modern fleets, what is the most important ship in a modern fleet? No. In Pearl Harbor, it was very fortunate for America that there were no ships of this type in Pearl Harbor. And this is used by many people to say that there was a conspiracy that they were deliberately out. The aircraft carriers. The aircraft carriers are the most essential parts of the fleet. And the aircraft carriers are protected with ships that are spread out all around it to make sure nothing comes anywhere near. And you have patrols hundreds of miles out of the aircraft carrier with orders to shoot to kill any threatening craft that's getting close enough to launch a missile. And so when you're trying to analyze something like this, if you have ships that are faster with greater range, the hope is you can just attack the enemy without risking them responding. And this was one of the big fears in World War II with the German ship Bismarck, that it had great speed and it had powerful guns that had greater range, that they were absolutely terrified of it getting out into the Atlantic. A lot of great movies and analysis of this. So we want to solve differential equations like this. And so as an example of what these can lead to is here is now 1,000 blue fighting 500 red. And before, 1,000 blue would go down to 500 after the battle. But now when you use this, it goes down to 866. Now you take the 866 blue and you fight 500 red, and it goes down to 707. And this is an incredible difference in result. So in the first case, you went down to 0. In this second case, 70% of your forces are still around. Again, depending on what numbers you use for your constants, you're going to get very different answers. But this shows you the ability of concentrating your forces and having multiple engagements can lead to a remarkable preservation of your force. So what I want to do is I want to try to solve those equations. As you would suggest, you're going to Mathematica, you can plug in all this stuff and Mathematica will solve it. I want to quickly go through it and show you how you would solve systems of equations like this by hand. And again, part of this is to prepare you for what math might you see after this, linear algebra, differential equations. These are really good next steps. So I have dB dt equals minus r times c. So I get dB dt equals negative c t, and I get dr dt is minus k times b of t. So unfortunately, these equations are more involved than what we had before. Last time we had, dy dt was either a function of t or a function of y and t. Now I have two different things, blue and red. And I have the derivative of blue is related to red, and the derivative of red is related to blue. I would love to get rid of the r of t in my first equation, but I don't know what r of t is. What do I know? I know dr dt. So what could I do to the first equation so I could then use my knowledge about dr dt? Okay, with respect to what?
R.
No. R is not one of my variables. T, right? Take the derivative of both sides with respect to time. So I would then get d squared b dt squared. Well, minus c is a constant, so it's just going to be dr dt. And d squared r dt squared is minus k db dt. Okay, well, oh, I know what dr dt is. It's minus k b of t. So I get d squared b dt squared is minus c times minus k b of t is equal to ck b of t. So I'm looking for a function. So I want to solve d squared b dt squared, or b double prime of t is ck b of t. So I want a function whose second derivative is almost the function back. It's the function multiplied by c times k. Can anybody think of a function that is close to solving this? Anybody think of a function, if I take two derivatives, it's close to itself? Could it be a polynomial? No, because what's going to happen to a polynomial if I take two derivatives? What will get smaller? The degree. So I'm not going to get back my function if it's a polynomial. What other functions do you know? Yeah, some kind of exponential. And if you think back, earlier today, when we're doing the method of divine inspiration, we talked about, oh, maybe the exponential, because I want a function whose integral is related to itself. Yeah, the exponential should have been on your mind. It's something we saw earlier today. And so now when we're coming over here, maybe an exponential is going to play a role. And so let's try. So this is divine inspiration. B of t is e to the at. Then b double prime, well, I'll do it slow. B prime of t is a e to the at. So b double prime of t is a squared e to the at is a squared b of t. So a squared equals what? CK. Okay, well, if a squared equals CK, then a is plus or minus, right? Or negative square root of CK. Because if I take two derivatives, I get a negative sign twice. This is the problem with divine inspiration. It's very easy to forget a solution. I could have just said, oh, my solution is e to the square root of CKT. But that would have missed the negative. So general solution, maybe I should say add because it's a naval problem, is b of t, is a1 e to the square root of CKT plus a2 e to the negative square root of CKT. And it turns out a differential equation involving one derivative has one free parameter. If you have two derivatives, you have two free parameters. It's like I need to give you, if I have just one free variable, if I give you my initial location, that's all I need. If it involves two derivatives, I need to give you my initial location, my initial speed. So over here, I have two free parameters, A1 and A2. If you think about it, you might argue that one of these parameters is 0. What should be true about the number of ships over time? They decrease. So maybe one of the A1 or A2 is 0. Which one might be 0? Maybe, which one might be 0?
A1.
Yeah, because what would happen if A1 is not 0?
It could potentially increase.
Maybe A1 is 0, as otherwise the number of ships goes to infinity as time passes. So you might say there are two solutions, but one of the solutions is not physically reasonable. But then you have to remember, but battle ends after finite time. So this goes back to, remember when I would walk into the wall to remind you that you have to check endpoints? Good, I'm glad everybody remembers. We can't have the battle running forever. What happens once the number of red ships is 0? The battle ends. You don't all of a sudden have, now there's -3 red ships involved in the battle, right? Once the red fleet is destroyed, the battle is over. So the time can't keep going. So yes, if I let time go to infinity, the A1 e to the square root of CKT, that's worrying me because the number of ships is going to just go off to infinity. But I can only use this equation up to a certain moment in time. This is very similar to when we use the geometric series. I have to make sure that if I want to use the formula, the absolute value of R is less than 1. So when I'm using this formula, I might want to say A1 is 0, but that would only work if I could let time grow arbitrarily. I can't, so this is not unreasonable. Okay. Any questions about this? So this is one of my favorite problems. I actually have not lectured on this problem since I think my first year at Williams back in 08-09 when I was doing differential equations in the spring. I absolutely love this problem in terms of it's a wonderful application of what we've been doing. It's a system of equations, so it's getting you ready for linear algebra. It's having us use our calculus techniques. A lot of it is, crying baby. The more times you hear the baby cry, the more times you can recognize. I want something such that the second derivative is a nice multiple of the first. In the first class, I'm going to suggest maybe it's a sine or a cosine, because two derivatives of sine is negative sine. Two derivatives of cosine is negative cosine. So it's similar, but not quite. And of course, it makes sense that this is not going to be sine and cosines, because what happens to your number of ships if it was sines and cosines? You have like this kind of periodic battle, which on physical grounds does not make sense. Exponential decay, that makes a lot more sense for what's going on. This is a really simple problem. We've removed a lot of complexities, but the goal is to show you how to start. You start with a simple model. If you can't even do the simple model, you have no chance of doing something more complicated. And here we can actually do enough on the simple model that we have some intuition as to what's going on. For the more complicated problems, all hail Mathematica or other programs, MATLAB, whatever, you can run simulations. And a lot of times if the calculation is too hard, do a million simulations. All right, so this is a good place to stop.